Hi everyone, this is a lecture on sampling distributions. I mentioned to you earlier that the video that is actually linked to the topic in the course outline was actually created a couple years ago before I had the technology that I have right now. Right now I have technology where the video could be a whole lot clearer. I could do it in 1080p. And so anyway, I needed to sort of just redo this. Sampling distributions. Now, in our last class, we talked about the normal distribution. And then in this class, we will actually look at the normal distribution in a different way. Not in a different way so much, but we will look at it in with respect to this concept called sampling distributions. In other words, we'll be applying it in another context. So just a quick recap. The normal distribution we said was a bell-shaped curve. All right, and that a lot of phenomena in real life can be modeled by the normal distribution, which is why it is so important. So the bell-shaped curve, it has a mean mu, standard deviation sigma, and we are often interested in the probability of observing a range of values for the random variable. So let's just call this one x1. Let's call this one x2. So I could be interested in the probability of observing a value that is greater than x2 or less than x1, or it could be between x1 and x2. And you may recall, to find those probabilities, what we used was the standard normal. In other words, we translated each of these x values to a z-score, and using the z-table, we could find areas under the curve. So that is the principle behind finding probabilities under the normal distribution. So we usually have a mean. So if, for example, my mean was $250 I spend per week, and with a standard deviation of 50, and say, what is the probability that in a randomly selected week I spend more than 300 and say $25. So my x in this case is 325, and so we would look at the probability of x being greater than 325. And then what we said is that we would actually convert this x value to a z-score. So it would be the same as saying the probability of z greater than or equal to, but what is a z-score? A z-score is the value of the variable minus the mean. In other words, the distance between the value of that variable and the mean, but we express it in standard deviations. So that would be the z-score. In this case, it would just simply be z greater than or equal to 325 minus 250 over 50. And if we calculate that, that would be 75 over 50, which would basically be that z would be 1.5. The probability of z greater than or equal to 1.5, and we simply look that up in the table. I'm not really trying to do a complete normal distribution problem, just to jog your memory very quickly. All right. So you may recall we did probabilities with the normal distribution, and we used the z-table to assist us with that. All right. So now let's get into, just before I go a bit further. In the case of the normal distribution, we are actually interested in a single observation. So for example, I am saying, what's the probability that a single week I spend more than $325? So I represent that by x. In other words, an observation of the random variable is $325 or more. That's what I'm looking for. So we're not really as such taking a sample larger than one. It's just a single observation. Now let's get into sampling distributions. What is that about? Well, if you really remember what statistics is all about, statistics is all about the idea that we want to take a random sample from a population or target population that we have an interest in, And in looking at the information from that sample, we learn something about that population. So now, instead of just taking a single value, or asking what's the probability of observing a value of the random variable greater than or equal to 325 in this case, we are now interested in taking a sample. And why would we take a sample? We take a sample because that sample is supposed to estimate for us values in the population. So out of a population of, let's say for example, 1,000 students, and they spend money every week on groceries, entertainment, toiletries, etc. And we could ask the question, then, what's the probability that a random sample, or not a random sample, but a randomly chosen student spends more than a certain amount of money, or less than a certain amount of money, or between one value and the next. But now, because statistics is about taking samples, I could take a random sample of, say, 50 students and observe the sample average and say, then what is the behavior of that average? What does that look like? So if I took 50 students and I average their expenditures, what does that look like? So let's get into the idea of sampling distributions, all right? Sampling distributions. So the reason why we are interested in sampling distributions is because when we do statistics, we take samples. And so we want to learn something about the behavior of samples or the nature of samples. So if this were my population, and say again we're looking at student expenditures on like groceries, toiletries, entertainment and so on. And let's just say per week students on average will spend $250 with a standard deviation of $50. So I'm just going to use that. So if I took a random sample from that population of a given size and n, but let's just say my n happens to be 100. All right? So in that sample of 100 students, I will ask them, how much money did you spend? And I would add up all of the values from the 100 students and average it. That gives me a sample mean x bar. We call that x bar, the sample mean. And you already know how we calculate, because we've already found mean and standard deviation for samples in chapter 3, I believe it was, when we're looking at measures of central tendency. And then there's also a sample standard deviation, because the 100 values, if we put it all together, we could actually get the standard deviation of that 100 values. So because it is a sample, we will call it S. We will not call it sigma. Sigma is for the population, mu is for the population, x bar is for the sample, S is for the sample. So x bar is sample mean, S is sample standard deviation. Now, if you think about this for a moment, we said that, there could be several thousand students. At St. Mary's, for example, we have about 10,000 students or more. So if I took a random sample of 100, I will make one observation. Perhaps my sample mean was 275, and my sample standard deviation was somewhere around $38, It's possible. What if I took another sample from that same population of the same size? Would I get the same answers? Answer is no. That different sample will yield different numbers. And then if I repeated that experiment, where I took another sample and another sample, as I keep taking samples, all the possible combinations of 100, I will get sample means, different sample means. And so if I took all of those sample means, let's just number them, x bar 1, x bar 2, x bar 3, x bar 4, x bar n, if n is my number of samples, or let's use m, because n is our sample size 100 in this case. So m would be the number of samples. These values have a distribution. In other words, they have a shape. I could actually draw a frequency diagram for these values and say the frequency of sample means between this range and this range looks like this, and then, you know, so I could have a distribution that looks like this. So that would be the nature or the shape of the distribution, but that would be for sample means, x bar. Not x as in the case of the population, but x bar. So that distribution of the values that we obtain from a sample gives us a distribution. So we call it a sampling distribution. Why? Because that distribution was obtained from a sampling process. In other words, we took a random sample of 100 each time, measured the mean. Another 100, measured the mean. So all of the means put together gives us that distribution. How did we get it? From a sampling process. So what do we call that distribution? A sampling distribution. All right? So that's where the term comes from, the sampling distribution. And so the question that we want to ask is, what is this sampling distribution like? What does it look like? We know that the population could possibly be like a normal distribution, but if I took those samples from the normal population, what would that distribution look like? What would it look like? So here's what we learned, right, about this, which is useful for us, is that we have two conditions. So if the population is normal, then the sampling distribution is also normal. So in other words, if I have a normal population and I'm sampling from that normal population, then my sampling distribution will also be normal. So here the random variable is x, but in the sampling distribution, the random variable was x bar, the sample mean. So all of the means have an average if we put them all together, so we call it mu x bar. And they have a standard deviation, which we call sigma x bar. So mu x bar, sigma x bar. So from the sampling process, if the population is normal, the sampling distribution is normal. So population, normal, sampling distribution is normal, which basically then gives us that the mean of the sample means happen to be the same mean as the population mean, and the standard deviation of the sample means turns out to be the population standard deviation divided by the square root of the sample size. So essentially what we have now is a different normal distribution. They have the same mean but different standard deviations. That sigma x bar up here is sigma over square root of n. So that's the relationship between that and the population. So what you can see happening to the standard deviation is as the sample size gets larger and larger, since n is in the denominator, the standard deviation, or the standard error we call it, of the sampling distribution will get smaller and smaller. So in essence, if the population looked like this, I'll draw that one in blue. If the population looked like this, in red the sampling distribution will look like this. It gets smaller, right? So, and then of course as the sample size gets bigger and bigger, it will have a narrower standard deviation. Okay, so as n gets bigger, that's the relationship between the two. Now, because that sampling distribution is also a normal distribution, it will have z-scores as well. It will have z-scores. So what would the z-score look like in this case? Z is equal to, so since our observation is now a sample mean, we will take the difference between the sample mean and the population mean. So the population mean would be mu x bar, and we will divide it and express it in standard deviations. So we're working with the sampling distribution right now. Remember that sampling distribution has a mean mu x bar and a standard deviation sigma x bar. So if I make an observation x bar, the z-score associated with that would be x bar minus mu, which is the distance from the mean, divided by the standard deviation. But because we have a relationship between the population and the sampling distribution, I could also express the z-score as x bar minus mu, because we know the population mean and the mean of the sampling distribution are the same, and then express the standard deviation of the sampling distribution, or the standard error of x bar, in terms of the population standard deviation. It would be sigma over root n. And so that is the case of the sampling distribution of the sample mean. If the population is normal, sampling distribution is normal. We have a name for that. Your book doesn't really name it, but we do have a name for it. It's called the first limit theorem. FLT, first limit theorem. So that is, if the population is normal, just to do a schematic of that, mu sigma, then the sampling distribution is also normal, mu x bar, sigma x bar. But then there's a relationship between them. What's the relationship? Mu x bar is equal to mu, and sigma x bar is equal to sigma over the square root of the sample size. That's the relationship between them. Now, remember I said the population is normal, the sampling distribution is also normal. What if the population is not normal? What happens to us then? If the population looks something like this, then, and I sample from that population, what happens to the sampling distribution? Well, it turns out under special circumstances, right, the sampling distribution could still look like this. So this would be the mean and standard deviation of the population, the mean and standard deviation of the sample means, right? And so it turns out that under special conditions, so what's the special conditions? So if the population has a mean and standard deviation as follows, but it is not necessarily normal, as long as we take large sample sizes, in other words, when we generate our sampling distribution, make sure your sample size is large. What is large? If n is greater than or equal to 30. So as long as the sample size is sufficiently large, our sampling distribution will start to look like this. All right? Which then gives us that the mean of the sampling distribution is also the same mean of that population, which is this mean right here. And the standard deviation of the sample means will be the standard deviation of the population divided by the square root of n. So look at that. So we have the same result, except that we require the sample size to be sufficiently large. So there is a theorem that supports this called the central limit theorem. The central limit theorem says if the population is distributed for mean, mu, and standard deviation sigma, then as long as the sample size is sufficiently large, the sampling distribution becomes approximately normal. And what does that mean? So once it's normal and we have the mean and standard deviation, we could find z-scores. So the z-score would remain exactly the same as before. All right? So z-score would still be x bar minus mu sigma over root n. And we would use that because I could ask you the question, if we go back to our problem about St. Mary's students spending money, that what if I took a random sample of 100 students, that the average expenditure for the 100 students will be between $275 and $300. So this is what I could be asking. But notice now it's different. I am asking what is the probability that the sample mean that I observe, if I took a random sample, that sample mean lies somewhere between 275 and 300. Now that's different from saying if I pick a random student, what's the probability that that student, one student, spend between 275 and 300? Okay? But then if I take a random sample of 100 students and I average the expenditures, what is the probability that the average expenditure for the 100 students is between $275 and $300, okay, dollars? So the first case, I am just dealing with the normal distribution of the population. Second case, I am dealing with the sampling distribution, which happens to be normal, because 100 is greater than 30. So I would satisfy the condition that the sample size is sufficiently large. Good. So that's what I want to do to introduce you to the sampling distribution of the sample mean. Sample distribution of the sample mean. So I'm going to go quickly through some terms, and then I'm going to work an example. After that, we will do the sampling distribution of the sample proportion. Okay, so let's do that. So a couple of terms are very important. Now let me just mention this now, and you may hear me mention that again and again. If you want to do well in statistics, you must learn the language. Listen to me very carefully. You must learn the language. So we know what a sample is. A sample is a portion of a population. The population is basically all the values that we are interested in. Now there is a term called a point estimate. A point estimate is the value that we get in a sample. In other words, when I take that sample from that population and I measure the sample mean, that sample mean is a point estimate. So in other words, X bar, which is a point estimate, estimates for me population mean. S, which is a point estimate, estimates for me population standard deviation. Anything we observe in a sample, we will observe in a sample is a point estimate of its equivalent in the population. So hence, we could have a sampling distribution of anything we observe in a sample. As long as we take multiple samples, then we are observing multiple values of that of whatever that variable is, and therefore it has a distribution which we call a sampling distribution. So sampling distribution of X bar, sampling distribution of P bar, which we'll come to shortly, which is for proportions. But for now, we're only dealing with sample means. So these are some terms. An element is an entity on which data is collected. So in a population, we have several elements, and we talked about elements in chapter 2. Population is a collection of all the elements of interest. A sample is a subset of that population. And then the sample population is the one that you actually drew your sample from. Okay? And a frame is a list of all the elements that the sample will be selected from. The frame. So if we're speaking of say all the students at St. Mary's, if we're going to target, if we're going to draw the sample from St. Mary's, then all the people at St. Mary's will then be the frame. Okay, and frame and population are not exactly the same, but they should be quite similar. So let's say we wanted to look at the views of students. But if we then decided to only look at the views of St. Mary's students, then our frame is St. Mary's. The question is, does St. Mary's students represent the population? Maybe not. So we have to be careful. The frame should look very much like the population. Okay. This says here that the reason why we collect sample data is so that we could learn about a population. That's fairly straightforward. And then we have to have different methods for obtaining samples. Point estimation is basically, as I already mentioned, is the value that you observe in a sample. All right. And you can see a simple example here where X bar is a point estimated mu. If we took a sample size of 30, the sum of the values was 50,520, then we get 1684. That's a sample estimate. And we could do the same for standard deviation as well. All right. Let's keep moving. And so these are that's just an example showing you the mean values for some SAT scores. And we look at the entire population, and then we took a random sample, and then we can get different values. Now always remember that what you observe in a sample is not always going to be exactly equal to the population value. It is an estimate of it. And if you have a pretty good sample, then your estimate should be pretty good. So if you see here, look, you could see 1684 is a pretty good estimate of 1697. 85.2 is a pretty good estimate of 87.4. And 0.67 is not that far off from 0.72. So point estimates versus population parameter. If we get a good sample, we would typically get fairly good results. So the sampling distribution of X bar was a process for making what we call or drawing inference about a population, because the whole reason why we take samples is so that in the sample, when we study it, we learn something about the population. Okay, so population mean mu is determined. That's the first thing right here. And then we take a sample from that population of n elements, and then we sample data provides a sample mean right here. And then that mean is used to make an inference about the population mean. So that X bar is supposed to make an inference about mu. So that's the process. I want to understand what is the average amount of money people spend on entertainment. Let me take 100 students and then sample them, find that sample estimate, and then that gives me information about the population. Do they spend a lot of money? Do they spend a little bit? Etc. All right? So that's all good. So I've already mentioned the sampling distribution of X bar, that there are two cases that we could talk about. So the sampling distribution of X bar, we would denote its mean by mu X bar and its standard deviation by sigma X bar. Population mean mu, population standard deviation sigma, and so forth. And the first limit theorem, which I've already mentioned to you, is that if the population distribution is normal, the sampling distribution of X bar is normally distributed. So you can see that right here in the first sentence. Okay? In most applications, the sampling distribution of X bar can be approximated by a normal distribution whenever the sample size is 30 or more. So they're jumping ahead because really we're speaking about the central limit theorem. So the central limit theorem says when the population from which we are selecting that sample, right, does not have a normal distribution, the central limit theorem is helpful in identifying the shape of the sampling distribution of X bar. So it says, in selecting random samples of size n from a population, the sampling distribution of the sample mean X bar can be approximated by a normal distribution as the sample size gets larger and larger. But we need to know when. When can we say, guess what? That sampling distribution is approximately normal, and that's when n is greater than or equal to 30. Okay? And from there, we could certainly go ahead and do some calculations. So that covers for us the basic idea behind the sampling distribution of the sample mean. And so now what I like to do is to work a problem for you. So in our problem set that I give to you, I want to look at problem number 24. So problem, let's do this again. So problem number 24, chapter 7. All right. The exact page number, I'm not sure, but it's problem 24. And I'm going to read the context for you. So if you could actually quickly go to chapter 7 and then look up problem 24, we will see what that problem looks like. So it says the following, right? Barron's reported that the average number of weeks an individual is unemployed is 17.5. So if we make a note of that, the number of weeks of unemployment, average number of weeks of unemployment. I will use an abbreviation, average number of weeks of unemployment is 17.5. So that's basically the population average, 17.5 weeks. Okay. we're told assume that for the population of all unemployed individuals, the population mean length of unemployment is 17.5, that the population standard deviation is 4 weeks. So we're told to assume population standard deviation is 4 weeks. So it says show the sampling distribution of X bar, where X bar is the average for a sample of 50 unemployed individuals. So our sample size is 50. So what's the sampling distribution of X bar? Here's what I'm going to do. X bar is a normal distribution, so I'm going to use some notation. Mu X bar, sigma X bar. So that's a nice, neat way to say that X bar is a normal distribution. Now, we were told that, we were not told, sorry, that the population was normal. We just told that we had a mean and standard deviation. So because our sample size is large, we could apply the central limit theorem and say that the sampling distribution is normal. All right. So if that is the case, what is mu X bar? Mu X bar is mu. What is sigma X bar? Sigma over root n. So I could actually continue this and say that's the same as mu sigma over root n. So it's normal with a mean of mu and standard deviation of sigma over root n. So that would be in terms of the population. And that's the notation for the sampling distribution. So that's the first part, part A. That's all we need to show. What is the probability that a simple random sample of 50 unemployed individuals will provide a sample mean within 1 week of the population? Within 1 week of the population. So if I draw that, I like to draw this diagram because if you don't draw it, sometimes you cannot see what you're looking for. So the mean is 17.5 weeks. Oops. Okay, that's better. And the standard deviation is 4. So mu 17.5 and 4. So so X bar must be within 1 week. So since we're talking about the sampling distribution, this is population, I need to put this as sigma over root n, which means that this is 4 over root 50. But the population mean, the means are the same. So within 1 week, sorry. So if I add 1 week, that becomes 18.5. And if I subtract 1 week, it becomes 16.5. So technically, what I'm interested in is the probability of being between 16.5 weeks and 18.5 weeks. So if I took a random sample of 50 unemployed individuals, what's the chance, the probability that the average unemployment will be between 16.5 and 18.5 weeks? And this is how I would write that down. So for this question, it will be written down as, let's go back to black, 16.5 weeks. And notice I don't put X this time, I put X bar, because that denotes that I'm looking at a sampling distribution. 18.5. All right. So to get that probability, I must convert these two X bar values to Z values. I must convert the 16.5 and the 18.5. So I'm going to generally refer to them as Z1, right? Z2. So in other words, Z1 corresponds to 16.5 and Z2 corresponds to the 18.5. That's the idea behind those two. And so I would need to calculate the Z values, but remember what our Z score looks like. Z score is just X bar minus mu sigma over root n. So if we wanted to put that together, that would be equivalent to the probability of 16.5 minus 17.5 divided by 4 over root 50, z 18.5 minus 17.5 divided by 4 over the square root of 50. And then we need to figure that out. Well, when we do the computation on that, it turns out that that is equivalent to z being between negative 1.75 and positive 1.75. Just move this, make some room. So if you do the computation, that's the same as the probability of z being less than negative 1.75. So all you have to do the computation. Negative 1 over 4 divided by root 50 will give you that answer. And the other side will be positive 1.75. So what do we do to get that information? If you look at your textbook and you look at the areas that you get under the normal table, and I'm going to pull it up just now so you could see. So if we did that, that was under the normal table, and this was negative 1.75, positive 1.75. You know that I'm going to do this in red. The normal table will give you the cumulative values. So all of this for the 1.75. In blue, it will give you all of this for the negative 1.75. So how do I get what I'm looking for, which I'm now going to shade in black, which is being between those two values? I must subtract, so this will have to be equal to the area associated with 1.75 minus the area associated with negative 1.75. So that's how I would do that. So now I must look up the table and find those values. So let's see if I could bring in my table. Bear with me. So I'm going to video or file. Let's see if I could bring the file in. And I could go here for the file. This is great. Well, let's go back because I don't want this. I want the tables. And here we go. And we get the Z table. So let's look up negative 1.75. So negative 1.75, let's choose that for a second. I'm going to add that to our content. Takes a second or two. So negative 1.75, if I scroll up here. And the way the Z table works, you may recall, on the top we have the second decimal place, first decimal place in the first column. So negative 1.75 is here. Sorry. It's this value right here, negative 1.75. 0.0401. And then if I keep going, I believe I'll get the other, there you go. I need positive 1.75. Positive 1.75, 1.7, I would go across. It is this value right here, 0.9599. And so to get the area in between the two, I need to subtract 0.0401 from 0.9599. And then that will give me the answer. So let's see, going back to our problem, this would be equal to 0.9599 minus 0.0401, and the answer is 0.9198. 0.9198, and that's the answer. So that's how you solve that problem. Okay. The question is saying, what is the probability that a simple random sample of 50 unemployed individuals will be within half a week of the population mean? That is exactly the same thing. And so we don't really need to do that one. But let's do this one instead. What's the probability that the sample mean will be greater than or equal to, and since we know that it's 17.5 weeks, so I'm just going to use let's just say 19.75 weeks. What is the probability of being greater than 19.75 weeks? Well, that would be the probability of Z greater than or equal to x bar minus mu sigma over root n, because we're talking about sampling distributions. In this case, what's my x bar that I'm interested in? It'll be Z is equal to 19.75 minus 17.5 over 4 divided by the square root of 50. Let's see what we got. So that looks like 2.25. This is going to be huge. Over 4 multiplied by the square root of 50. I brought the root 50 on the top. Let me grab my calculator so I could calculate this for you. 2.25 multiplied by root 50 equal divided by 4, and the answer is 3.97. So that's a fairly big Z. So that 3.97 is actually quite a number, in the sense that it would basically amount to an outlier. It would amount to an outlier because remember we said beyond 3 standard deviations we have an outlier. So that means that the probability of getting this sort of sample would be very small. It's an outlier. Let's figure that out. Now, our textbook unfortunately does not have Z values that large. So we are interested in the probability of x bar greater than or equal to 19.75. That is equal to the probability of Z greater than 3.97, greater than or equal to 3.97. So let's take a look. And so we have to try to find 3.97 from our diagram. But if you look, what's the largest value that we have? The largest value that we have is 0.9990 when the Z value is 3.09. 3.09. So at 3.09, the area in the tail is 0.9990. To get to 3.97, we have to keep going. So if we're going to keep going, what will happen to the area in the tail? It will be smaller than the difference between 1 and 0.990. So let's take a look at that, what that looks like on the diagram. So what we're essentially saying is this, that if we are interested in this probability of 3.97, correct? Now, at 3.09, this area shaded in blue is 0.9990, which means at 3.09, the area left to the right of 3.09 would be, and I'm just going to do it like this. That area is going to be 0.001. That's what that area is. In other words, if I shaded that in, let me just dot that. It would be all of this right here. Everything going to the right, okay? 0.001. However, I am not interested in that area. I'm interested in this area shaded in black right here, the very little piece, right? Because that is the area to the right of the 3.97. The table does not have a value for me, so what can I say? I could certainly say that that area is smaller than 0.001. So therefore my probability of Z greater than or equal to 3.97 is less than 0.001. And that's the answer. So that's really calculating probabilities when we're going to need an inequality, because our table does not work very well. Now if we want to use Excel, Excel could actually give us the exact value. And I did not calculate the exact value for Excel, but certainly Excel can do that for us. And I will show you in a separate video how to find normal probabilities and so on using Excel. So we could have, other similar questions like, what is the probability that the average for the random sample will be less than, instead of 15.75 weeks. 15.75 weeks. And we could do the same thing, calculate the Z value and so forth, right? And once we get the Z value, in that case our Z value would be negative, so the area in the table on the negative side will give us exactly what we're looking for, which is the area in the tail right here. So I would suggest for practice that you try problem number 25. Okay. Problem number 25. The College Board reported that the following mean scores for 3 parts of the Scholastic Aptitude Test (SAT), and we had 502, 515, 494. The standard deviation is 100, right? And so what's the probability a sample of 90 test takers, so that's our sample size n, will provide a sample mean test score within 10 points of the population mean? So I just kind of frame that one for you, but I want you to actually solve it yourself. Okay. So if we were looking at which one is the first part, it has to do a mean test score within 10 points. Okay. Of the population mean of the 5. Okay. So population mean 502. That's for reading. Standard deviation is 100. All right. And so within 10 points, here and here. So 10 points would basically take us to 512. If we subtract 10 points, it would be 492. So you want the probability of X bar being between 492 and 512. Okay, and we could certainly go ahead and calculate that, just like I've demonstrated. So I think what I'm going to do here is pause, and then we'll create a separate video on proportions, sampling distribution of sample proportions. So that was sampling distribution of sample means. It's very important that you review this, because our next topic now is we're going to take that information that we get in a sample and do what we call an interval estimate for the population mean. Good? Okay, if you have any questions, please send me an email and I'll try to respond as quickly as I can. Thank you very much.